such that their sum is 1, total weight is 1. We take these as lambda. So, I will call lambdas this pair. Then we define the weighted arithmetic mean, this is the definition, to be lambda 1 A1 plus lambda 2. When we had equal weights, lambda 1 is half, lambda 2 is half, that was the classical arithmetic mean, A plus A2 by 2. And similarly, we define this, the weighted geometric mean, to be A1 power lambda 1 times A2 power lambda. Again, when you take lambda 1 equal to lambda 2, you get the standard geometric mean, square root of A1 A2. So, this is a weighted geometric mean and weighted arithmetic mean. The question was, is the weighted mean also the arithmetic geometric mean inequality hold? This was the question that we asked. Okay. So, now we will look at this question. Well, this is true if and only if, let us first write what it means. That is the left hand side, this is the right hand side, lambda 1 A1 plus lambda 2 A2. Okay. Again, I will write in bracket, without loss of generality, assume A1 A2 greater than 0, because if any one of them is 0, again it is obvious, geometric mean is 0 and therefore inequality holds. So, in all these cases we are assuming this to be non-zero, and we are assuming so it is strictly 0. So, without loss of generality, assume A1 A2 to be 0, then this is a real number, that is a real number. So, x is less than or equal to y, if and only if the log x is less than or equal to log y, because the log is also a monotone increasing function. So, this is true if and only if log A1 lambda 1 A2 lambda 2 is less than or equal to log lambda 1 A1 plus lambda 2 A2. So, now let us take the logs. So, it is lambda 1 times log A1 plus lambda 2 times log A2 is less than or equal to log lambda 1 A1 plus lambda 2. So, therefore, the weighted arithmetic geometry mean boils down to this, the logarithm I pointed out in the beginning of yesterday when we started discussing inequality. So, therefore, all I have to do is verify whether this is true, whether that is true. So, if we prove this inequality, then automatically the geometric arithmetic mean is proved. Now, it is obvious from the graph of the thing, then we will prove an analytic also. I will carefully show you an analytic proof also, little bit clear. How does the graph of logarithm look like? It starts off at 0 at minus infinity and goes like that. Okay. Now, if you take any 2 points, to show it very clearly, we will draw yes, 2 points, real numbers A1 and A2 without loss of generality. If A1 is equal to A2, nothing to prove. Again, without loss of generality, A1 is different from A2 and both are greater than 0. So, suppose A1 is here and A2 is there, then this is log A1, this height, this is log A1, and that height on the y scale is log A2, right. What this point is simply a point somewhere in between. That is when lambda 1 A1 plus lambda 2 A2, since A1 is less than A2, this will be less than lambda 1 lambda 2 A1, that is lambda 1 plus lambda 2 into A1, which is A1. So, this is less than greater than A and less than A2. So, this point here, if I call it as x, that lies here, and therefore log x is here, and log x is actually a point there between A1 and A2, which is again a combination of this. So, that is exactly what we are trying to say, that when the point lies here, the corresponding will lie there. Okay. So, let us get this straight. So, what we will do is the following. Again, without loss of generality, A1 not equal to A2, because if A1 equal to A2, everything is obvious, and one of them must be smaller. So, without loss of generality, assume A1 is smaller than A2. Then we have A1 here, A2 there. Now, take any point between A1 and A2, T. Okay. So, let us T belong to A1, A2. Then let us define phi of T to be 1 over T. So, that is a function now defined for T moving from A1 to A2. So, this is a function phi of T is defined for T of A1 and A2. Now, take a point between these two, that will be of the form lambda 1 T plus lambda 2 A2. See, this point lambda 1 T plus lambda 2 A2 is greater than lambda 1 T, and A2 is greater than T. Lambda 1 plus lambda 2 is 1. So, this is greater than T. Less than. So, it is a point that lies between T and A2. Now, define a function psi of T to be 1 over lambda 1 T plus lambda 2 A2. Now, I have to, right. Now, T is smaller than this, therefore, 1 over T will be greater than that. So, therefore, psi of T will be less than psi of T will be less than phi of T. T lies to the left, so the inverse will lie right, 1 over T. Okay. So, now integrate. There are all are continuous functions, because A1 is positive, everything is well defined. So, if I have two continuous functions, one curve lies always strictly above the other curve. So, the areas will be correspondingly maintained. So, the integral A1 to A2 psi t dt will be strictly less than A1 to A2 phi t dt, because they are all continuous functions. Okay. Now, all you have to do is write it down explicitly. That is integral dt by lambda 1 t plus lambda 2 A2 A1 to A2 is less than A1 to A2 dt by t. What is the integral of this? Put this as some u and do all the integration. It is 1 over lambda 1 log lambda 1 t plus lambda 2 A2 for t between A1 and A2 is less than log t. So, it is log A2 minus log A1, or you take the lambda 1 to that side, simply look at what you get, lambda 1 A2 plus lambda 2 A2 minus log lambda 1 A1 plus lambda 2 A2, take the lambda 1, that is positive, so you can push it to the other side. Okay, so now it is only a simplification. Lambda 1 2 into A2, lambda 1 plus lambda 2 is 1, so that log lambda A2 log lambda 1 A1 plus lambda 2 A2 is less than lambda 1 log A2 minus lambda 1 log A1. Take this to that side, others to this side. There is 1 here and there is minus lambda. And okay, let me first take log. This one comes here as lambda 1 log A1, and then the log A2 term, this and this combined give you 1 minus lambda 1 log A2, and that goes to the other side, lambda 2 A2. Now use the lambda 1 plus lambda 2 is 1, so 1 minus lambda 1 is lambda 2. Strictly less than log lambda 1 A1 plus lambda 2. And that is what star was. So, when does equality take place? When they were different, the areas are going to be strictly above, and when they are equal, automatically equal. So, star holds and equality holds if and only if A1 equal to A2. Proof star. Okay. So, therefore, we can now summarize and write our inequality. G lambda is less than or equal to this. Equality holds if and only if A1 equal to A2. Okay. So, the weighted means also maintain the same inequality. The geometric is at most arithmetic, and the geometric will match the arithmetic mean only when the two numbers are the same. Okay. We will come back to means a little later, more means. Okay. But let us now use these two simple means to get some standard inequalities which are useful in analysis. So, we will now look at some applications of these arithmetic geometric mean inequalities. Okay, first we will apply the standard arithmetic mean geometric mean, that is without the weights. So, this is 2, this is 3. So, first let us apply 2, the standard arithmetic mean geometric mean. Okay. So, I will carry on in simple steps before we reach there. Okay. Suppose I have a vector with n components, okay, and a vector y with n component such that they are all real and greater than or equal to c. Okay. They are all real and non-negative. So, I am looking at, say, suppose you are in 2 dimensions, 2 of them are there. I am looking at vectors which are in the first quadrant. Okay. And if you are in 3, you are looking at the first octant. Okay. Xi, yi, zi, all 3 components are positive, not negative. Okay. Now, what I am going to do is, let me define alpha I to be xi squared and beta I to be yi squared. Still positive, no problem, everything is positive. Now, alpha I and beta I are positive, so I will take A1 as alpha I, A2 as beta I, and apply the A. So, by 2 with A1 equal to alpha I, A2 is equal to beta I, what do we get? The geometric mean is less than or equal to the arithmetic mean. But what is the geometric mean? Square root of alpha I must be less than or equal to alpha I by 2 plus beta I by 2. but alpha is x square, xi squared, beta is yi squared. So this is xi yi. This is less than or equal to xi squared by 2 plus yi squared by 2. Okay. So it's just apply the arithmetic geometry very clever of A1 and A. The arithmetic mean itself is the clever choice of applying x and applying 0 less than or equal to x square. The fundamental inequality is 0 less than or equal to x square. Now, for every component we can do that, I equal to 1 to n. Okay. This is true for 1 less than or equal to I less than or equal to n. Let's add all these inequalities. So we get, adding all this, we get summation xi yi I equal to 1 to n is less than or equal to I equal to 1 to n x squared by 2 plus summation I equal to 1 to n yi squared by 2. Now let us assume that the vector is unit length in our normal sense. X1 squared plus x2 squared plus xn squared is 1 and y1 squared plus y2 squared plus yn squared. So suppose further that summation I equal to 1 to n xi squared, summation I equal to 1 to n yi squared are both 1. Okay. Then what do we get? Summation I equal to 1 to n xi yi is less than or equal to half plus half, that is 1. Right. Okay. So shall we write it here now? Number 4. X is equal to x1, x2, xn, y equal to y1, y2, yn, xi, yi greater than or equal to 0, summation I equal to 1 to n xi squared equal to 1 is equal to summation I equal to 1 to n yi squared. All these imply summation I equal to 1 to n xi yi is less than or equal to 1. When does equality take place? Right in the first step we must have equality. And there arithmetic and geometric mean equality means alpha I must be equal to beta I. This must happen for every I. Xi squared must be equal to yi squared for every I. They are all non-negative. Therefore xi must be equal to yi for all I. That means x and y must be the same vectors. So equality holds if and only if x is equal to so that's our first inequality. So we will push ourselves. We have now put lot of restrictions on the components, non-negative, and they must have length 1. Now I will try to lift the condition that the length must be 1 and subsequently lift the condition that they must be non-negative by everything reducing again and again back to this case. So now we look at, we remove, we have only this, okay, we may not have summation I equal to 1 to n xi squared equal to 1 equal to summation I equal to 1 to n xi squared. So therefore I must somehow bring it to this case. So whenever you have a vector whose length is not 1, you bring it down to a vector of length 1 by dividing it by the length. But in order to divide by the length, I must make sure that I am not dividing by 0. So I must assume that the vectors Afterwards, we will take the case when one of the vectors is 0. So, without so suppose x, y are non-zero vectors. So, now what I am doing is I am taking positive vector. Now, I am really in the first quadrant or the first octant. Okay. Previously, in the first, what is that? The unit cube or surface of the unit cube in the first quadrant or the first octant, but now I am allowed to wander around in the first octant and the first quadrant. Suppose x, y are non-zero vectors, then let u be equal to u1, u2, un, v be equal to v1, v2, vn, u equal to ui equal to xi by square root of summation I equal to 1 to n xi squared, vi equal to yi by summation I equal to 1 to n yi squared square root. Okay. So, I have divided the vectors by their length. So, now what can I say about u and v? They satisfy all the conditions for 4. Their components are non-negative, they have length 1. So, I can apply 4 with u for the uv vector. So, apply 4 to uv vector. What do we get? Summation ui vi I equal to 1 to n is less than or equal to 1. Right. Now, ui is xi and vi is yi. I will take the denominator to the other side. Okay. See, when I write like this, it is now obvious that if one of the vectors is a 0 vector, this fellow is 0 and that fellow is also 0. So, no problem, it holds. Okay. Now, the vectors is the 0 vector equality. So, we condition was only for this manipulation, but once you reach this step, it is valid even for one of the vectors is the 0 vector. Okay. Now, that is the generalization of the previous fellow. Now, where does the equality take place? If it has to take place here, that is the uv case. That means ui must be equal to vi. ui equal to vi means xi must be equal to this number divided by this number into yi, which is every component of x is the component of y, which means they are linearly dependent, and that is the case even if one of them is 0. So, equality depend only if ui equal to vi for every I, that is xi equal to some k times yi for every I, where k is the yi. That is a number. Now, all the numbers have been added up, that number depends, that is a constant now, it does not depend on I. Okay. So, therefore, x, y linearly depend. Okay. So, now we have got the next stage of this game, that we will call as phi. So, what do we have now? X equal to x1, x2, xn, y equal to y1, y2, yn, all are n component vectors, xi, yi greater than or equal to 0 implies summation I equal to 1 to n xi yi is less than or equal to summation I equal to 1 to n xi squared square root to summation I equal to 1 to n yi squared. Now, this becomes a special case of that, with this length being equal to 1. Okay. All right. So, now we have moved to, from here we removed one condition. Now, we are going to remove the non-negativity condition. We want to remove the non-negative condition and get some kind of inequality for all vectors. Okay. That is our next stage. So, what we do is take a vector x1, x2, xn, y equal to y1, y2, yn and rn. I am not putting any more conditions, non-negative, like that. Okay. So, when we wanted to prove this, we reduced it to this case. Now, when you want to prove this, we reduce it to this case. So, here we converted the vector to a unit vector. Now, we want to convert it to a vector which is negative, because the moment you have non-negative, 4 can be like 4 open. Okay. So, let u be the vector where ui is mod xi, vi is mod yi. Now, you see, therefore, I am not worried. I have made everything non-negative. So, ui greater than or equal to 0, vi greater than or equal to 0, therefore, can apply phi to uv vector. So, what you get? So, in place of x and y, you must write u and v. Summation I equal to 1 to n ui vi is less than or equal to summation I equal to 1 to n mod ui squared, square root of summation I equal to 1 to n mod vi square. But no mod is needed, yes. Well, even if I put, it's not a sin. Okay. Mod ui is the same as ui. Okay. Mod ui squared and vi, mod ui squared and ui squared, ui is real, so it does not matter. Okay. So, now let us substitute, that is summation I equal to 1 to n, what is it, ui is what? Mod xi and the other one is y. So, mod xi into mod yi is mod xi yi. That is less than or equal to square root of summation I equal to 1 to n mod xi squared into square root of I equal to 1 to n mod yi squared. Okay. Now, I am going to do the next thing. I look at the mod outside. Summation I equal to 1 to n mod xi yi is less than or equal to modulus of a sum is less than or equal to sum of the modulus, and that is less than or equal to this. So, what did I get? So, I get summation I equal to 1 to n xi yi is less than or equal to summation mod xi squared square root the square root of mod squared. How many places we need to have equality for this to happen? First of all, the equality must happen here, the equality must happen there. When does the equality happen here? That is our fourth case. That is, the u vector and the v vector must be multiples of each other. That only says mod xi is alpha times mod yi. Sometimes it may be plus, sometimes it may be minus. So, we are to still not sure whether x and y are linearly dependent. But then when does equality holds here? But if you want this Equality, both should be in the same direction, not that direction. So each must be a positive multiple of the other. Okay. So here each must be the possible multiple of. In the other case, the moduli is a possible multiple of the other. Combine the two, you will get they will be linearly dependent. So therefore, we have our, this is the fundamental inequality, which is, I will first write, implies, call it as 6. This is one of our first fundamental. Summation moduli I equal to 1 to n xi yi is less than or equal to summation I equal to 1 to n mod xi squared square root summation I equal to 1 to n mod yi squared. Equality if and only xy linearly defined. And this is what is known as the Cauchy-Schwarz inequality. And this is a simple consequence of arithmetic geometric mean. You just go on using arithmetic geometric mean, you will get this. Okay. So this is the Cauchy-Schwarz inequality. One of the Cauchy-Schwarz. We will generalize this later. The Russian name for that is Bunyakovsky's inequality. More popularly known as Schwarz inequality, sometimes Cauchy's inequality, sometimes Cauchy-Schwarz inequality, sometimes Cauchy-Bunyakovsky-Schwarz inequality. Yeah. Any question? So we have applied the arithmetic geometric mean to get one of the standard inequalities in which is probably used umpteen number of times in analysis. One of the most fundamental inequalities. Okay. We will see in fact to further extensions of this, which is the broad Cauchy-Schwarz repeatedly used. You will see more and more generalizations of this as we go along. Okay. Now, what happens if these are complex? This inequality holds still, and again equality holds if and only if all the complex numbers are positive multiples of one direction, right? So this holds. From here everything is real, so we can apply. So the result is true even for complex. So R. So there is no problem about this also. Whenever you have a real or complex n component vectors, we have this inequality. Okay. This is the generalization of the two-dimensional vector. We have that x dot y is equal to the length of x into the length of y into cos theta, and since modulus of cos theta is less than 1, modulus of x dot y is less than or equal to the length of x into the length of y. That generalization is this inequality. Okay. Now let us take a bit of the out of the generalized arithmetic geometric mean inequality, the weighted arithmetic geometry. What do we get out of that? Okay, so we will get generalization of a more general version of the Cauchy inequality. We will call it. It is called the Holder's inequality. Okay. Now you will see that we will follow the same procedure. I will just indicate this side, this step, and once we go to the step where we have the lengths are 1, the remaining, then go to the next case where the length is made 1, and then go to the next case where everything is made positive, and the same order of will give you the remaining results. Okay, so the crucial step is to prove for unit vectors with positive coefficient. Okay. So once again, let us take x equal to x1, x2, xn, y equal to y1, y2, yn. They are all real. Xi, yi greater than or equal to 0. And okay, I will not write anything else now. Okay. I go there is a feedback. Now, let us take a weight. Now we are going to take a weighted, where lambda 1, lambda 2 greater than 0 and lambda 1 plus lambda 2 is 1. So, I am going to apply the weighted arithmetic geometric mean repeatedly. That is the idea. So, now lambda 1 is less than 1 because the total sum is 1. So, lambda 1 is less than 1. I will call P as 1 by lambda 1, Q as by lambda 2. Okay. And then P is greater than 1, Q is greater than 1, 1 by P plus 1 by Q equal to 1. Okay. So, when two real numbers P and Q are greater than 1, and if the reciprocals add up to 1, they are called conjugate to each other. Okay. So, P and Q are said to be conjugate to each other. Okay. Now, I am going to define the numbers. Let us see. I am going to define alpha I to be xi to the power of 1 by lambda 1, yi to the power of 1 by lambda 2, which is xi to the power of p, yi to the power of right, xi to the power of p, y to the power of q. Then apply 3 is the weighted arithmetic geometric mean. What do we have? G lambda. Let us take A to be alpha I, A1 to be alpha I, and B A2 to be beta I, and apply geometry. So, they have a G lambda A is less than or equal to A lambda. Okay. But now let us write out what is G lambda A. G lambda A is A1 power lambda 1, A2 power lambda 2 less than or equal to lambda 1 A1 plus lambda 2, the weighted arithmetic mean and the weighted geometric mean. What is this? A1 is alpha I power lambda 1, beta I to the power of lambda 2 less than or equal to alpha I to the power of, what was A1? A1 was alpha I plus beta I. Okay. What is alpha I to the power of lambda 1? Xi. Beta I to the power of lambda 2, yi, less than or equal to lambda 1 xi power p plus lambda 2 q, y power q. Is that okay? Now, this is true for all I. So, add up all of them. What do I get? Summation I equal to 1 to n xi yi is less than or equal to lambda 1 summation xi power p I equal to 1 to n plus lambda 2 I equal to 1 to n yi power p. Now, yi power okay. So, just like previously we assumed that the sums were 1, I am going to assume that this sum is 1 and that sum is 1. So, assume summation I equal to 1 to n xi power p is 1 is equal to summation I equal to 1 to yi power q. Then what happens to the right side? Just lambda 1 plus lambda 2, but lambda 1 plus lambda 2 is 1, and therefore we get summation xi yi. When will equality happen? Again go back, xi will be allowed to be equal to be yi. Okay. So we have the seventh inequality. Shall I write x equal to this 1 over p q greater than 1 over p plus 1 over q equal to 1, and then summation xi power p equal to 1, summation xi yi to the power of q is also equal to 1. So all these conditions imply summation I equal to 1 to n xi yi is less than or equal. And equality okay. What will you do next? If this is not 1 and if this is not, make the x's as 1 by dividing this by to the power of over p and y over q, therefore that becomes 1. So next case is x equal to x1, x2, xn, y equal to y1, y2, yn, pq greater than 1 over p plus 1 over q equal to 1. That implies summation xi yi equal to 1 to n less than or equal to. Previously the denominator went to the other side and gave us this product. Now what did it do? Other square root I will get to the power 1 over p. So that will become summation I equal to 1 to n xi power p to the power of 1 over p, summation I equal to 1 to n yi to the power of q 1 over q. Of course, I have forgotten that fact that xi yi greater than or equal to 0. Okay. Now what is the next step? To remove the non-negativity, so that we can now state the result for all vectors. How do you remove the non-negativity? Look at the moduli. Okay. So as in step 5 to 6, we get this is the next important inequality called Holder's inequality, which says that xy belongs to, again we can have Rn and then Rn to Cn also, because the modulus things work. Rn or Cn implies, and 1 pq greater than 1 over p plus 1 over q equal to 1 implies summation xi yi I equal to 1 to n modulus is less than or equal to summation I equal to 1 to n xi to the mod xi to the power of p to the power of 1 over p into summation I equal to 1 to n mod yi to the power of p. Equality equal only xy. This is called the Holder's inequality. So if you put p equal to q equal to 2, you get the Cauchy-Schwarz inequality. That is lambda 1 equal to lambda 2 equal to half, which is the same thing as saying p equal to q equal to 2 is the case. So this is only a special case of the Holder's inequality with p equal to q equal to 2. Okay. So these are two important inequalities, namely the Cauchy-Schwarz and the Holder's inequality. Next I will prove one more inequality which is called the Minkowski's inequality. Okay, that's the crucial inequality for us. So that these inequalities play a very crucial role in the analysis of functionals on finite dimensional spaces. Okay, then we will lift ourselves to the case where we will allow infinite number of components and get Cauchy-Schwarz, get Holder's inequality, and get Minkowski's inequality when we have infinite component vectors. And this will play a crucial role while analyzing functionals on infinite dimensional spaces. Okay. So next, so I will erase all this because now I have no more space to save all the inequality. So I will go back to the first page and then start from here. And this is called the Minkowski's inequality. Okay, so again I am going to look at x equal to x1, xn, y equal to y1, y2, yn, all are in Rn or Cn. Take any two vectors, n component, the components can be complex. Now, mod xi, okay, once again let us take p to be greater than 1. Okay, there will be a corresponding index q that will not appear, you will use it. Okay, so let us take p is greater than 1 and q the corresponding conjugate index. What does that mean? 1 over p plus 1 over q is equal to 1. Q is greater than 1 and 1 over p equal to plus 1 over q equal to 1. We will bring it in somehow. Now, look at first look at this mod xi plus yi. Okay. And I will take the power t. Okay, you see what we are trying to do shortly. This I will write as mod xi plus yi to the power of p minus 1 into mod xi plus yn. Nothing surprising. I just took one term out and remaining power there. Because p is greater than 1. So there is at least one there, I pulled it out and the remaining powers I kept there. So mod xi plus yi to the power of p minus 1 into this. But this is less than or equal to mod xi plus mod yi. That is okay, right? There is no problem about that. Now, therefore, I will write it as mod xi plus yi to the power of p is less than or equal to mod xi into mod xi plus yi to the power of p minus 1 plus mod yi into mod xi plus yi to the power of p minus 1. Okay. So I can add all of them. Okay, I added all the inequalities from I equal to 1 to n. Look at the Holder's inequality. If all are positive, non-negative, I don't have to put the modulus here. Okay. So suppose I had non-negative, the Holder's holds for the modulus. Now take mod xi to be the first factor and this as the second factor. So, let alpha I be equal to mod xi, beta I to be equal to mod xi plus yi plus the power of p minus. So, therefore, by Holder, summation alpha I beta I, I do not put modulus because alpha I and beta I are non-negative. Okay, that less than or equal to summation I equal to 1 to n. What does the Holder's inequality say? Alpha I to the power of p to the power of 1 over p. So, it is alpha I to the power of p to the power of 1 over p times beta I to the power of q to the power of 1 over q. Now, let us substitute for alpha I and beta I. So, therefore, summation I equal to 1 to n mod xi into mod xi plus yi to the power of p minus 1 is less than or equal to summation I equal to 1 to n. Alpha I is mod xi to the power of 1 over p, and what is beta I? Mod xi plus yi to the power of q to the power of, to the power of p minus 1 into q to the power of 1. Correct? Now, what is that? That is equal to summation I equal to 1 to n mod xi to the power of p to the power of 1 over p into summation I equal to 1 to n mod xi plus yi is p minus 1 into q. Look here, p plus q equal to pq, right? So, q is equal to pq minus p equal to p minus 1 into q. So, p minus 1 into q is just is it equal to p to the power of p to the power of q. So, p minus 1 into q is equal to p. No, is it equal to q or p? Okay, I will keep the p here and take the q there, then it is p minus 1 into q is equal to p. Very simple manipulation. Okay. Right, so we have got this. Similarly, if I replace the xi by yi, I will get this term to be yi to the power of p. Similarly, summation mod yi to the power of times mod xi plus yi to the power of p minus 1 is less than or equal to summation I equal to 1 to n mod yi to the power of p to the power of 1 over p times the same term, because it is the same term for both. So, what do I get from these two? In the right hand side, this term is smaller than that and this term is smaller than this, and therefore, we get summation I equal to 1 to n mod xi plus yi to the power of p, this left hand side, is less than or equal to the sum of these two terms. In these two terms, this it out summation I equal to 1 to n mod xi plus yi to the power of p to the power of 1 over q into summation I equal to 1 to n mod xi to the power of p to the power of 1 over p plus summation I equal to 1 to n mod yi to the power of q to the power of 1 to the power of p for 1 over p. We are almost done. This term and this term, right? So, we will bring this fellow to this side. What do I get? summation I equal to 1 to n mod xi plus yi to the power of p to the 1 power here and a minus 1 over q will come this side. So, what is 1 minus 1 over q? Is precisely 1 by p. Is less than or equal to summation I equal to 1 to n. Okay, and this is what is known as Minkowski. All these cases, equality will hold. It would only be linearly dependent. You will trace back all the places equality and you will get that. So, that is what is known as the Minkowski's inequality. So, now I lost the number. So, this is called Minkowski. Which means xy belong to Rn or Cn, PQ greater than 1 over P plus, okay. I will just P greater than 1 is enough for me. I will write first P greater than 1, summation I equal to 1 to n implies mod xi plus yi to the power of P to the power of 1 over P is less than or equal to summation I equal to 1 to n plus summation I equal to 1 to n mod yi to the power of q to the power of 1 over q. Equality depend only if xy is linearly dependent. When p equal to 1, this is obvious. See, when p equal to 1, what happens? Mod xi plus yi is certainly less than or equal to mod xi plus mod yi, add them. So, p equal to 1, it is obvious. So, therefore, I can write the p greater than or equal to 1, this is true. Okay. Let us call the Minkowski's inequality. So, these are three fundamental inequality: the Cauchy-Schwarz, the Holder's inequality, and the Minkowski's inequalities, and they are all consequences of simple arithmetic geometric mean. Holder, the Cauchy-Schwarz is standard arithmetic geometric mean. Holder is the weighted arithmetic geometric mean consequence, and Minkowski is consequence. So, at the root of the AIM, and below that is the root x squared is greater than or equal to 0 and equal to 0 if one is x equal to 0. They will not be true. Okay, the inequality need not be true, because remember I have used the fact the arithmetic geometric mean. There I have used certain things about the logarithmic function and the function 1 over t. Okay. Now, subsequently these all mean certain amount of terminologies like concavity or convexity. That power p less than 1 does not give that particular property, and therefore this whole thing collapses. So, we need what do you mean? No, you can manipulate, because suppose the components are 0. Okay, so many components are 0, then what is going to happen? Okay, so that's the problem. So, in p greater than p less than 1, all kinds of funny things can happen. So, the best thing is to avoid them. Okay. Okay, and for our purposes, these are the things, some of the standard examples. Okay, so what this will give us is a number of examples of metric spaces, nonlinear spaces, also Hilbert spaces, which are the, and more importantly, this will give us the structure of functionals in these spaces. Okay, so now we have consolidated the fact. So, look at this, consolidated the fact that we talk about the Schwarz type inequality, Holder type inequality, Minkowski type inequality, for vectors with finite number of components. Now we will push our luck and see whether we can get something similar to this for infinite component vectors. That's, I remember there was a conference several years ago on functional analysis in the Delhi University. The vice chancellor at that time was one Professor Udit Narayan Singh, who was a functional analyst. So he organized the conference. At the end of the conference, the last day afternoon, he asked us whether we can have a general discussion on the curriculum that we should have for functional analysis courses in our universities. And it was everybody welcomed the idea, and the afternoon session started, and one of our very senior professors was asked to, very good analyst, was asked to chair the session. And he started the session with the chairman's remark. The first remark he made was, non-trivial functional analysis starts when linear operator theory ends and non-linear operator starts. More importantly, when bounded operators end and unbounded operators start. And most of the fellows who presented the paper in the conference were those who worked on bounded linear operators. So more or less I dismissed all of them, saying that you are not fit to talk about functional analysis. Now, I taking the cue from him, I will say non-trivial beginning of functional analysis starts with infinite dimensional spaces. So therefore, these inequalities we must at least generalize to move towards the simple vectors with infinite number of components. So to that end, we have to go to this idea of extending these inequalities for infinite component vectors. So towards this end, let us first start with the sequences. That is, a sequence of components are there, and these are all vectors in Rn or Cn. Say that again. I am sorry, not Rn and C. I will not use any symbols, okay? X, J, Y. I will use symbols later. R or C. Okay. Okay. Now let us look at this. Suppose we want to get an inequality similar to Minkowski. Let us go backwards. Just now we saw Minkowski's inequality. How should it look like? So how should it look? Okay. So something like this. What was the old case that we had? PQ greater than 1 or P greater than 1, summation I equal to 1 to n mod xi plus yi to the power of P less than or equal to summation I equal to 1 to the power of 1 over P mod xi to the power of P to the power of 1 over P plus summation I equal to 1 to n mod yi to the power of P to the power of 1 over P. This is what we had for finite case. So now what we would expect is we want something like this, right? We would like to have something like that. there is a huge problem. Huh? Instead of which one? No, yeah, that is what we symbolically we write as a series. Okay, right. Now look at that right hand side. If any one of these sums is infinite, the right hand side is infinite, there is nothing great about it. Okay, but it may happen that this and this are finite. We don't know whether that is going to be finite or infinite. So we have to worry if one of them is infinite, one of these sums is infinite, there is really nothing to prove. The right hand side is infinite, less than infinite, not a big deal. So the non-trivial one we have to worry about is when both of them are finite. So if either summation I equal to 1 to infinity mod xi to the power of p or summation I equal to 1 to infinity mod yi to the power of p is infinity, then nothing to prove. So we have to look at xy such that for both these two are finite. For both that must be finite, and then see whether we get. It is trivial. One of them turns out to be infinite. So the non-trivial question that we should look at is if x and y are two sequences of real or complex numbers such that that sum and this sum are finite, then does such an inequality hold? Okay, that's the question. So now let's look at how we will do it. Now you see, when this and this are finite, that means the right hand side is already finite. Therefore, we must assure first of all that finite. Okay. Now, to assure that the left hand side is finite, it's enough if without the power 1 over p I say it is finite. If this is finite, to the power of 1 over p is also finite. So to say that this is finite, I must say that series converges. So I want to assure that the series mod xi plus yi to the power of p converges. So therefore we should know what is meant by saying a series is convergent. When does the series converge? When the sequence of converges. In this case, sums go on increasing or at least non-decreasing because every term is non-negative. So I have got some sum, I am going to add one more term which is non-negative. So the partial sums are non-decreasing. A non-decreasing sequence will converge if there is a upper bound. So if we show that the sequence of partial sums are bounded, what is meant by partial sum? Summation I equal to 1 to n. Suppose I show there is a number k such that summation I equal to 1 to n, this is finite, I am finished. Okay. So if in this case RHS is less than infinity, this below. Okay. Let me call it as RHS of 1. RHS of 1 is finite. We want to make sure first that LHS is finite. Okay. That is, for this it is enough if we show summation I equal to 1 to infinity mod xi plus yi to the power of p is less than infinity. Okay. For this since terms are all non-negative, it is enough if we show there exists a constant k independent of n, okay, such that, of course, that summation I equal to 1 to n mod xi plus yi to the power of p for every, okay, that is the idea. If you show that the partial sums are all bounded, then the series of non-negative terms is forced to be convergent. You see how cleverly we brought down the problem to looking at a sum which is only of terms. You see, we have more or less brought the problem to a finite case. Okay. Now therefore, let us look at this. So now if we look at summation I equal to 1 to n mod xi plus yi to the power of p to the power of 1 over p, since there are only 5 now, I can apply old Minkowski, that is less than or equal to summation I equal to 1 to n mod xi to the power of 1 over p plus summation I equal to 1 to n mod yi to the power of p to the power of 1 over p by Minkowski. Okay. This is true for every n. Whatever finite n we choose, we can apply Minkowski. But now what can I say about the right hand side? Any finite sum is less than or the corresponding infinite sum. Let us call this as x and this as y. X is given to be finite and y is given to be finite. So x plus y is what I call as k. So therefore, summation I equal to 1 to n mod xi plus yi to the power of p to the power of 1 over p is less than or equal to x plus y. And we are done. And not only that, we can now let n go to infinity, and what do we get? What we are looking for. Let n go to infinity, you get this inequality. Partial sums are bounded, and therefore the least upper bound must be smaller than or equal to any bound, and it's okay. So therefore, let n go to infinity. The general Minkowski's inequality. So the general Minkowski's inequality we will state now. Minkowski. Is p greater than 1, summation xi to the power of p I equal to 1 to infinity is less than infinity, summation I equal to 1 to infinity mod yi to the power of p is less than infinity. All this implies summation mod xi plus yi to the power of p to the power of 1 over p is less than summation I equal to 1 to infinity mod xi to the power of p plus summation mod yi q to the power of p. Now with that notation we can simply say x plus y. This is for the vector x plus y, this is for the vector x, this is for the vector y. Okay. For the vector x, I wrote mod xi to the power of p to the power of 1 over p. For the vector y, I wrote mod yi, and for the vector x plus y, I will have to write xi plus yi. This is roughly the idea. Okay. So that is the general Minkowski. One step further up now, we have got into infinite component vectors. Whenever x and y are such that their pth power add up to finite, the sum will also, the pth power will add up to finite. This of the sum will be less than or equal to p power individual sum. Okay. When p equal to 1, that is the obvious inequality. Okay. If summation xi is finite, summation yi is finite, summation mod xi plus yi is also finite. So therefore, we can even write p greater than or equal to 1 also. P equal to 1 case it is obvious. So this is called the Minkowski. So what it says is, if you take this sum as the measure of such a vector, what measure? You call it a length measure or whatever it is, some kind of a quantification of the vector x, and this is the corresponding quantification of the vector y. These quantifications are induced by a number p, which is greater than 1. So this is the p quantification of x, the p quantification of y, p quantification of x plus y will be less than or equal to the p quantification of x and the p. This normal modulus x plus y less than or equal to modulus x plus modulus y. Modulus is one quantification. Okay. That is now general p quantification of vectors, and even that language, the p quantification of a sum is less than or equal to the individual p quantification. That is what Minkowski's inequality is. This will tell us, we will see put them all together later and see that such vectors form a vector space. This makes us not only they form a vector space, and in that vector space this acts as a quantification or a notion of length. That is what is known as normed linear space. So we will look at those formal definitions later. That is why we need all these inequalities. Similarly, at least may not have, I will not have. Similarly, let us look at holder. So in the infinite case, what are the finite case holder? That is less than or equal to summation I equal to 1 to n I equal to 1 to n mod yi to the power of q to the power of 1 over q, where these p and q were conjugate, 1 over p plus 1 over q must be. Now therefore, what we want is, if I now take the infinite number of components, is this true? That is what in infinite dimensional space. Once again, if one of them is infinite, it is trivial. If one of those sums is infinite, the right hand side is already infinity and everybody is going to be smaller than him, no problem. So the non-trivial case is when both of them are finite. So non-trivial question is, these two are finite, then is it, what is the procedure? First we must take left hand side to be finite. For that we must show, we can't say that now this is a non-negative sum. So what do we do first? First you put this, and then that is bounded above, and when that is, this is bounded above, that series converges, this absolute convergence we have. Once we have absolute convergence, anything will converge, and therefore the sum of any such sum will be. So similar thing is called the, this is called the, it is true, and that is, we will quickly see it next time, and that is called the Holder's inequality for the infinite case. And in the special case, p equal to q equal to 2, we get the Cauchy-Schwarz inequality. Okay. So that is the standard length, summation mod xi squared, I equal to 1 to infinity square root. Okay. So the corresponding, so p equal to q equal to 2 will give us the Cauchy-Schwarz. So So therefore, starting from this generic inequality, x squared greater than or equal to 0 if and only and equal to 0 if and only if x equal to 0, we get a series of inequalities lifted step by step. Arithmetic geometric mean, weighted arithmetic geometric mean, Cauchy-Schwarz, weighted Cauchy-Schwarz which is hold there, and then Minkowski, then go to infinite components. We have got a whole list of fundamental standard inequality. We can get see, for example, what are all these? They are all averages. See, everything started from average. Arithmetic average is 1, geometric average is 1. So the geometric average and the arithmetic average are compared. We got inequalities. We can now generate a number of averages from this idea. So there is a whole family of averages. It is not just geometric, there is not just arithmetic. We can generate a whole family of averages, and we can talk about the various. It says is jocularly that in every problem some average will give a good result. Okay. So if arithmetic average is bad, try geometric average. See, suppose we say average score is 35, it's a good performance. But if you take arithmetic average, it may come out as 34.7. So it will reflect as a bad performance. But therefore you take geometric average. That's going to be smaller. And if that's not good, take some other average which will make smaller. Okay. So there are a huge number of averages. So when somebody says on an average it is good, we don't know what he is talking about. Unless he tells me what is the average in which it is good. So therefore this word, the word mean is very mean. Okay, unless it is explicitly told what it is, we don't know what it means. Okay. So we have to be very, very careful. Alright, so we will now possibly, in the next class, I'll assume this Holder and Cauchy-Schwarz because the arguments are the same. So therefore we have all these inequalities, and I will just indicate, okay, the next step. See, in all these cases, what we have done is, we have 1, 2, 3 n components, then 1, 2, 3, 4, 5, 6, 7, 8 n, etc., infinite number of components. What if we have a continuum of components? We get to the notion of functions. See, after all, okay, 1 minute. You can take the vector 1, x1, x2, etc. We can think of this as a function from the set 1, 2 and any sequence, etc. to the real or complex numbers. And the value at 1 is called the first component, the value at 2 is called the second, is called the component. So instead of this, suppose I have an interval I on the real line, and I look at functions, real or complex valued functions, and now can I ask something like Minkowski? What does the Minkowski say? If I have two such functions, what should that be replaced with? Integral over I of mod xt to the power of p is finite, and integral over I mod yt to the power of q is finite, or that is also finite. I will just look at Minkowski. Then the question is whether integral over I mod xt plus yt to the power of p to the power of 1 over p is less than or equal to I mod xt to the power of p dt to the power of 1 over p plus the y term. Okay. Of course, the problem comes with what integral are you talking about. So all this business of which integral, let's say suppose for the time being f and g were continuous functions, then the normal Riemann integration we can do, and we can ask these questions. Okay. Now the answer turns out, previously what did you do? We wrote the arithmetic geometric mean, we added all of them. Now we add the arithmetic geometric mean, integrate both sides. You get the standard inequalities for at least these functions for which function makes sense. Next, okay. So we'll now get more Holder's inequality, Minkowski's inequality, and Cauchy-Schwarz inequality for functions also. So we will get vector spaces, etc., which are infinite dimensional, which are function spaces. So we'll get a number of examples that will be available for us to work with. These are all classical examples of metric spaces, nonlinear spaces, Banach spaces, Hilbert spaces. We'll use them to get the right type of space. So we must have at least a whole collection of examples for us to understand our abstract theory of functionals. Okay. Okay. So next class, what I will do is I will spend short time on these things, then to metric space, of functions.